Now we need to move on to our final talk of this plenary session. Today this will be a talk given by Michelle Leroux. Michelle is from NOAA CPC and will talk about prediction, predictability, and data assimilation for tropical Pacific and its teleconnections. So thank you, Michelle.
All right. Thanks so much for having me at this meeting. This is actually the first TPOS related activity I've attended. So I'm really looking forward to learning from everyone more about observing systems. So I am a forecaster of NOAA Climate Prediction Center. We are adjacent to the Environmental Modeling Center. And we work a little bit with the modelers. I'm not a modeler myself, but I certainly have a lot of colleagues like Arun Kumar and Kai-Hong Nguyen and Jason Zhu who kind of work at that intersection of our analysis and also models. And I really want to credit these other folks too for aspects of the forecast, diagnosis, and so on. So why do we care about ENSO? This is sort of a given here at NOAA Climate Prediction Center. It's a very key component to our seasonal climate outlooks. That, along with climate trends, are the two most important sources of skill. So we track it very closely for that reason. And in support of this, we run the North American Multi-Model Ensemble, or NME. This is run in real time for the benefit of operations. All models are due in by the 6th of the month, and they come from folks like GFDL, University of Miami, the Canadians, and NASA. The ENSO CFSv2 is a contributor, and I'll be drilling down a little bit on that particular model in this talk. You can also, if this interests you, you can download the forecast data. Both hindcast and real-time forecasts are available at the IRI data library. Increasingly, there's interest in ENSO predictions, in part because of the information they provide on ocean biogeochemistry. Obviously, the carbon and oxygen reservoirs are really important to marine ecosystems and fisheries. For example, El Nino can lead to higher partial pressures of oxygen, which actually causes an eastward shift of skipjack tuna and yellowfin. And also the Eastern Pacific is quite important, providing source waters for the California undercurrent, which can, of course, have important implications for the oxygenation and acidification of the ocean, which can impact fisheries. So in this talk, we're going to look a little bit more under the prediction hood. One thing I want to emphasize is that running a model in real time is very different from running it in hindcast mode or in a free run style. It is, it's one thing to have a model and it's another thing to have observations. It's quite a different animal to be putting both together in a real-time framework. And so warts arise, and those warts can be instructive, and I'm going to share some with you because we've started noticing some of these warts, especially when we compare our models to the North American Multi-Model Ensemble, or NME. And so this really does help us flag some errors, which I will go into. So in this talk, I'm going to be talking a little bit about CFSv2 resets that have been happening in real time periodically. This has caused some issues in our ENSO forecasts. These resets are implemented because of this cold bias that is arising in the Atlantic. We don't know why this cold bias is arising. It's still a mystery to us, but it's something that we have to fix in order to sort of address these problematic ENSO forecasts. And so here's a concrete example of one of these. This is model runs in early 2016. So we are coming off the very strong 2015-16 El Nino. And we had a reset in late March. And the reason we had that reset was because what you see right there, CFSv2 is predicting an El Nino. So we were coming off essentially the peak, and so the ocean was discharging, but our CFS model was instead counterintuitively predicting an El Nino. It wasn't until April that it settled down and started correctly forecasting a La Nina in line with the other NME models. And so what happened here was essentially large cold biases in the tropical Atlantic Ocean basically caused the modelers to do this reset. And top panel there is GODAS, which is an ocean-only assimilation system. The Atlantic was just kind of a mixed bag of weak anomalies, but CFSR, which is the initial conditions for CFS, had very, very cold anomalies extending through the subsurface and also along the equatorial Atlantic. And so after the reset, basically it went back to anomalies that are more similar to what you see with GODAS. So why did we do this reset? Again, it was that Atlantic Ocean cold bias that pushed us to do this. There's only really one source of documentation for this, the link above, and it was essentially a Weather Service memo pointing out that this was an issue and that a fix had been tested that reinitialized the ocean initial conditions in the operational CFS from offline GODAS. But what does this mean? What's the bottom line? Well, CFSR is the reanalysis and essentially the initial conditions for the CFS version 2 model. EMC actually maintains a separate offline global ocean-only system reanalysis, has the exact same oceanic inputs as it's in CFSR. And when these large Atlantic differences arise, essentially prior to the next simulation cycle, EMC replaces this with the offline ocean analysis. And this is fundamentally the reset. But keep in mind, the reset is global in extent. All right, so even though it's motivated by what's happening in the Atlantic, we're essentially plugging in this offline ocean analysis. And so if there's any differences between the two reanalysis, we can see differences. And this has a lot of implications, as I'll show you. So here's another example where we had a reset. It was in late January of 2015. So it was actually before the example I showed earlier. And in this particular example, CFS was actually tracking what occurred in the observations fairly well. This was not what the rest of the NME was predicting. The rest of the NME was not quite catching on to the potential of an El Nino so early. It shortly did after this cycle is through. But I was interested in perhaps capturing, using the model data itself, these resets. And I realized very quickly that I couldn't just look at this as a function of error in CFS, because there are times where this Atlantic bug actually leads to a better forecast, getting the right answer for the wrong reasons. So then I decided, okay, let me look at how this compares to another baseline. Let's look at the NME average. And keep in mind that forecast runs can jump around naturally, but my question here is, where is CFS jumping more than the NME average? And to do this, I basically decided to take the difference between two different runs. So here, I took the root mean squared difference along the trajectories from March and April. You see a very big jump there. And then in the NME, a much smaller jump. And so I'm curious in the times that CFS has a bigger jump than NME. And I decided to create a little time series of that. And that's what's shown here for the period from 2015 through the present. And what I found very interesting when I did this analysis is how much alignment there is between the resets and also these large run-to-run jumps in CFS, sometimes much larger than NME, like the case in March and April 2016, which is exceptional and is actually off this plot here. And as you can see here, there are resets that are not accompanied by a large jump in CFS. So it's certainly not a given thing. It seems to me when I look through the time series here that these jumps tend to be larger when they occur earlier in the calendar year. I'm going to go ahead and zoom in on this most recent jump that occurred in early 2021. Again, here's the Atlantic cold bias arising, and this is analysis by Kai Hong, and she showed that after this reset, we actually had cold biases jump into the Western Pacific here. And again, that's because this offline assimilation system was sufficiently different in the Pacific Ocean so that when it was reset, the biases immediately emerged. And so again, the reset was on the 15th of January, and we had this essentially huge shift toward colder conditions along the thermocline and above the thermocline. And as you can imagine, that manifested in CFS forecasts. The longest leads at the time in early January were actually a suggestion for maybe a little bit of a double dip La Nina. We can't verify this yet because this is obviously hasn't happened yet in the longest leads. But after the reset, boom, we had a really strong push toward a very strong La Nina. So this is an example where the oceanic assimilation systems and errors in it have really impacted the CFS forecast. And so after the reset, and eventually it did, go back into an equilibrium, where we were back to a borderline La Nina. But for a month or two there, we had pretty odd forecasts coming from the CFS systems. So what's going on with CFSR and our assimilation system? Arun Kumar, Jason Zhu, have talked with folks, and basically the bottom line is we don't know. It's really hard to diagnose this at an operational climate center, a weather and climate center, because a lot of the efforts are focused on the next generation of weather and climate models. It's possible there's just a big, instability, and if the forecast departs too much from the observations, or the observations don't exist, then the assimilation system just can't correct for it. It may be due to river runoff, leading changes in salinity. We're really not sure. And this leads to some follow-up questions that I hope the workshop participants are willing to discuss, which is the observing network sufficient to understand these coupled errors in reanalysis? Keep in mind that the observing network may be perfectly fine, and maybe it's a problem with the assimilation system itself. Does this error source from the ocean, the atmosphere, the land? Should we be resolving smaller scale processes? Is it in the correct location? So ultimately, where do we go next? What I like about this is that you can leverage NME and compare these individual models and kind of find these bugs that are happening in real time. Bugs are very instructive. And keep in mind, even though I focused on CFS version 2 here, this is happening at other modeling centers too, and they have their own strategies to deal with these real-time bugs. Should we be more routinely monitoring and advertising them? I think the answer there is, for most of this audience, probably yes, but keep in mind that it's important to consider how to incentivize this, because no one really wants to show off bugs or warts. And they also tend to be very focused on their own system and not necessarily comparing it with the other NME models. Should we be recommending targeted observations with these differences? Let's just think about how we can strengthen the linkages between the data assimilation and predictions. And I go to a quote from Tony Barnston: performance in a real-time setting is the ultimate test of the utility of long lead forecasts. It's, we can have the best modeling system in the world, but if we don't have great strategies to plug the observations into the model systems, then we'll obviously see things degrade. So just keep that in mind as you're having these discussions at this workshop. Thank you so much.
All right, thank you, Michelle. We have a question in the chat. I'm not positive. I think it may be from Magdalena Balmaceda from ECMWF. If not, you can correct me. But the question is, first, did you say that the need for the resets usually comes from cold conditions in the Atlantic? So in some of the examples you showed, that's true. Is this true generally? But the main question is, if so, do you have any idea what causes this problem and why this problem appears in the CFSR and not in the ocean-only reanalyses?
Well, CFSR is coupled to the ocean, at least for small periods of time. It's not really pure coupled data assimilation. We still have a need for that. But there is a point around the 6-hour guess forecast where there's coupling of the ocean. So since we're relaxing to just a ocean only assimilation, one would guess that some aspect of the coupling in CFSR may be the problem. It's also possible that there's just a lack of observations at small enough resolutions to resolve this. And then there was, of course, the fact that forecast models have biases. And if they have really strong model biases, then fundamentally, that can the assimilation system won't be able to keep up. It will gravitate toward those biases. So it could be a mixture of all of the above. There could be all sorts of issues going on with this couple system.
Okay, Tony Rosati has a question. His question is, why is this reset problem unique to NCEP? And I think I would maybe follow that up asking, first of all, is it unique to NCEP, or is that the impression we get from just from the examples you showed us?
Yeah, yeah, I don't think they are. I know that, for example, there's some issues with the NASA system right now. If you compare a NASA model to the rest of the NME, they've been having some pretty strong errors since they went real time. Their hindcast was, one situation. Their real time forecasts are a very different situation. I mean, the fact is, we just don't advertise it that much. I'm a forecaster, so I notice these when I create the month-to-month ENSO forecast. And so, of course, I work with my colleagues like Rujation and Kaihong and, ask what's going on here. But I mean, it's really, I think it's somewhat of a mystery of how each center deals with it. But I think they're happening at a lot of operational centers.
Thank you. Yosuke Fuji of JMA MRI has a question for you. First, he says, thank you for your interesting presentation. Do you check the analysis increments before the reset, and are they increasing?
That's a good question. I don't know. So what I would recommend, because Arun and Jason and Kaihong have been looking at this a lot closer, is if you have questions about the details of the data assimilation system, go to the Slack channel and type it in there. I'm hoping one of them can maybe ask someone about that. I don't know off the top of my head.
All right, thank you. And then the questioner that I believe is Magdalena, I'm sorry, the initials are NB8, asks, is NCEP the only system with a pseudo coupled DA system? So possibly this is why it may be more volatile than other systems. So I guess that's more of a comment than a question.
I think that's a really intriguing question. Maybe because we didn't go all the way. There's some issues there, but definitely put your comments in the Slack system. We can have a vigorous conversation about it with people who are a little bit more expert at this than I am.
Great. And so we still have time for another question. This is from Boris DeWitt, who thanks you and asks, what would you recommend in terms of observing strategies for the Far East Pacific where models have difficulties in forecasting?
Yeah,
no
so
pressure.
Yeah, there's a lot to unpack there. I mean, obviously, I think when we're talking about observing systems, it's really important to know what we're trying to predict. What are we really after here? For something as large scale as ENSO, it can be very hard to design a system, in part because there's already a lot of redundancy. So even if a tau buoy is out in the Eastern Pacific, sometimes we're okay because there's other observing systems that are compensating, and we don't notice any problems in the forecast. Like the real bad tau problems in 2012 through 2013 that an earlier presenter brought up, at that time we weren't noticing huge swings in the forecast, and that could be because the redundancy was really it was enough to get ENSO, or it was a problem that was impacting all models to the point where doing this sort of comparison between an individual model and NME doesn't work because it impacts every single system. So maybe we were missing something there, but I think you know, it's a tough question, and we should always be clear about what we're trying to forecast.